Okay. So
Yeah,
it's a pleasure to have you here.
Yeah, thank you. Yeah, as you can see, I want to talk about longer gaps between values of binary quadratic forms. And this is joint work with Christian Elsholz from Graz, Alexander Kalminin and Sergei Konyagin from Moscow, and James Maynard from Oxford. Okay, let me set the scene. So suppose S1, S2, and so on is the sequence of positive integers arranged in increasing order. And one of the questions you could be interested in is the gaps between two consecutive elements of that sequence, especially small gaps and large gaps. One case that has been extensively studied is the sequence of prime numbers. There is the famous prime number theorem. So the average gap between consecutive primes is of order of magnitude log Pn. There's also quite a few famous conjectures. For example, you have the twin prime conjecture. So this is the question about small gaps between consecutive gaps. One of the first results there was by Hardy and Littlewood in 26. So they could show under assuming the generalized Riemann hypothesis that you infinitely often get a gap which is 2/3 of the size of the average gap. So it's a small gap in that sense. The first unconditional result was by Erdős in 40. So he could show that infinitely often you get a gap a little bit larger than the average gap for a small positive C without needing to assume the Riemann hypothesis. And in the following decades, work focused on improving, numerically improving that result, getting a bit bigger constants C. So quite influential paper of Bombieri and Davenport on this topic appeared in the 60s. And also Helmut Meyer and other people, Janusz Pins, worked on this. And then so 20 years ago, a series of big breakthroughs started. So Goulston, Yildirim, and Pins, they were able to show that you infinitely often get a small gap, which is only of the size approximately the square root of the size of the average gap. And then even more spectacular results were achieved 10 years ago independently by Chang and Maynard. They could show that you infinitely often get bounded gaps between consecutive primes. And then in a polymath project, finally, that constant C2 was reduced to 246. And that's, as far as I know, currently the state of the art. Okay, so that's a summary of what is known regarding short gaps between consecutive primes. Regarding large gaps, one of the early results was by Erdős and Rankin. So they got this bound infinitely often. You get a gap which is a little bit larger than the average gap, which is log Pn. You get this extra term there. And again, for a long time, the only progress was in improving that constant 1/3 in front. It was a famous open problem. I think it was a $1,000 problem by Erdős, actually, to improve on that result, get a better order of a bigger order of magnitude for the size between for large gaps between consecutive primes. And a few years ago, in another big breakthrough in this area, Ford, Green, Konyagin, Maynard, and Tau, they were able to get rid of the exponent 2 here in the denominator. So this is the current the state of art regarding large gaps between consecutive primes. So now in this talk, I want to focus on the situation where we are not dealing with primes, but with the sequence of positive integers that are sums of two squares. And you can ask the same questions there, of course. You can ask about small gaps between numbers that are sums of two squares. And this question is not so hard to answer. For example, it's quite easy to show you infinitely often get gaps just of length 1. In fact, you can prove a pretty precise statement. So if k is a given positive integer, then you can show infinitely often k occurs as a gap size between consecutive numbers that are sums of two squares. And you even can prove this in a quantitative way, like here. Let me briefly sketch the idea how you can prove such a result. This can actually be proved by the circle method. And the ideas going in will actually also be useful for what we will be doing in the following. So let's fix that gap size k. So this is now a fixed quantity, and then choose a set of k minus 1 primes, p1 up to pk minus 1, that are all congruent 3 mod 4. And then the idea is to consider the following Diophantine problem. That's a system of one Diophantine equation and k minus 1 congruences. So the first Diophantine equation is telling us we have a difference of two sums of squares, which is k. And these congruences here are telling us, so this is the smaller of the two numbers that are sums of two squares. If you add L, and now L ranges in that interval, that gap interval, where you don't want to get a number which is a sum of two squares, then this congruence is satisfied. And because this is congruent PL mod PL square, and the p's are congruent 3 mod 4, this is telling you that number here can't be a sum of two squares. So this way, you make sure within that gap, you won't find any number which is a sum of two squares. And now, of course, you need to make sure this Diophantine problem actually does have a solution. And it's not hard to show there is no local obstructions. And then for this type of problem, then you have a local global principle. And actually, you can use the Hardy-Littlewood circle method to get quantitative results. The congruence conditions here can be turned into congruence conditions mod for x3 and x4, and then you can just apply the circle method machinery. This epsilon here on the previous slide, this is coming just from the fact that the same number can be represented in many different ways, possibly as a sum of two squares. So you have to take account of that. Yeah, and so this way, using the circle method, you can prove the result I mentioned on the previous slide. So I did that maybe 10, 12 years ago in a joint paper with Jörg Brüdern. So small gaps between numbers that are sums of two squares, they are pretty well understood. So let's now focus on the question of large gaps between numbers that are sums of two squares. So for large gaps between numbers that are sums of two squares, one of the first results was an unpublished manuscript by Turan. And a little bit later, Erdős published that result here. So infinitely often you get gaps of that size. So for numbers that are sums of two squares, the average gap now has a size, the square root of log Sn. So this is considerably larger than the average gap. And 30 years later or so, this was improved by Ian Richards. So he got rid of the square root log Sn and even got a very explicit constant, that constant 1/4 there. Yeah, so this is so far state of the art for large gaps between sums of two squares, and the situation is a little bit similar to the situation of primes. We are currently in this stage where we try to improve that constant because it looks hard to get a bigger order of magnitude, especially the Ford-Green, Koniagin, Maynard, Tau technique doesn't seem to carry over from primes to sums of two squares. Yeah, so in fact, Richards proved a result which is a little bit more general. The result he proved was the following. If you fix a fundamental discriminant D, then you can consider the sequence S1, S2, S3, and so on. That's the sequence of positive integers, which are represented by any binary quadratic form of discriminant D. And again, you can ask for large gaps in that sequence, and he obtained that result. And that's a straightforward generalization of this result on gaps between numbers that are sums of two squares. So if you specialize to that binary quadratic form x squared plus y squared, this has discriminant -4, then you exactly recover the 1/4 from above. Yeah, this is the first result I want to present today. So let S1, S2, and so on be the sequence of positive integers which are sums of two squares. Then we can improve the 1/4 in that result by Richards. We can improve it to this constant here. So the 0.25 gets replaced by approximately 0.868. I also have some numerics. I didn't compute very far. Probably this can be taken much further. So if you look up to 10 to the 10, then in that range, the largest gap between two consecutive numbers, which are sums of two squares, you can find is actually 105. There's also some conjectures based on probability theory, what you should expect, and the numerics is quite agrees with that predictions. We also have a result in the general case. So Richards considered a situation where you say got a fixed fundamental discriminant, and you consider the increasing sequence S1, S2, and so on of positive integers that can be represented by any binary quadratic form of discriminant D. And then Richards got for that lim sub here, he got a lower bound of 1 over the size of the discriminant. So this actually, for larger discriminant, gets smaller, which is a little bit disappointing. We can improve this. We can't completely get rid of the discriminant on the dependence on the discriminant, but the dependence has become now quite mild. So here, d minus 1 over phi of d, phi is Euler's torsion function. This is almost constant. So you have this almost constant term in the numerator, and then roughly divided by 2 times the logarithm of the discriminant. We have a slightly weaker result in A, which has the advantage of being completely explicit. There is no big O term in A. So asymptotically, B is the stronger result, but A is completely explicit. Yeah, so the 1 over D in Richards' result can be improved roughly to 1 over 2 times the logarithm of D. Okay, that's our second main result. And I thought I can talk a little bit about actually the techniques of proof. So let me first sketch the idea of proof of the Richards 1/4 result. So let's fix any positive epsilon, and let's fix the gap size k. And now we do the following for each prime congruent 3 mod 4. Let beta p the maximum exponent such that p to the beta p is at most 4k. And we consider this product. We take all the primes which are at most 4 times the gap size and are 3 mod 4, and we take them to that exponent plus 1. We will see in a minute why we want plus 1. And then we solve this congruence here. P is an odd number, capital P is an odd number, so we can solve this congruence for some y which is at most p. And then the claim is none of the numbers in the interval from y plus 1 up to y plus k is actually a sum of 2 squares. How can we prove this? Well, we consider the number 4 times y plus j, where j ranges over that interval, and modulo capital P, this is congruent 4j, and the 4y is congruent minus 1. So this is a clever construction Richards introduced. So this mod P, this is 4j minus 1. And now 4j minus 1, this is a number which is congruent 3 mod 4. So there must exist the prime P, which is 3 mod 4, and divides that number 4j minus 1 to an exact odd exponent. Let's call that odd exponent alpha. And now by definition of beta p, because that 4j minus 1 is at most 4k minus 1, this alpha here, that exponent can be at most beta p. And therefore the capital P is divisible by that p to the alpha plus 1. So from this congruence, we can infer also the number 4 times y plus j is divisible by p to the alpha. Alpha is odd, but it's not divisible by p to the alpha plus 1. And because p is 3 mod 4, that means that number 4 times y plus j on the left-hand side, it cannot be a sum of 2 squares. And therefore also y plus j cannot be a sum of 2 squares. So it remains to estimate the size of that y. So, and to estimate the size of y, we need to bound p. We can bound p to the beta p plus 1 by 4k in brackets square. That looks a little bit brutal, but right now it's pretty much the best we can do. So bounding p to the beta p plus 1 by 4k square, and then applying the prime number theorem in arithmetic progressions, we get this upper bound for capital P here, at least for sufficiently large k in terms of epsilon. And then we can solve for the gap size is at least log p over roughly 4, and y was at most p, so k over log y is at least 1/4 apart from that epsilon. And this way we get that Richards bound. So infinitely often we find a gap of size 1/4 minus epsilon times log Sn. So that lim sub is at least 1/4. Okay, so that's the idea of Richards' original 82 paper, and now the question is, can that be improved? And this can actually improve by 2 independent techniques. We called one of them a modular refinement, and the other one the probabilistic refinement. And you might ask, why does the paper have so many authors, 5 authors? Because these 2 refinements were found by different subsets of us 5. And then we joined forces and turned it into one paper. So in both cases, the idea is for a fixed gap size k to reduce the size of that product capital P. And let's first discuss the modular refinement. So for the modular refinement, so we've seen above, we are in that interval of length k, and for each j inside that interval, we found the number 4j minus 1 is divisible by a prime 3 mod 4 to an odd exponent alpha. So we can write it in this form, and r is a number which is 1 mod 4. Now let's suppose here the left-hand side 4j minus 1 is composite. Well, if 4j minus 1 is composite, then either r is bigger than 1 or alpha is bigger than 1. Also, both could be true. If r is bigger than 1, because it's 1 mod 4, it has to be at least 5. So it's very easy to see the prime has to be less than 4/5 times k in that case, because j is at most k. This number here is at most 4k minus 1. And if it's composite, then this prime here has to be less than 4/5 times k. So therefore, primes 3 mod 4, which are in that interval, which are close to 4k in that sense, they are only needed once in the argument from above, namely when that number 4j minus 1 is equal to p. And now it turns out we can arrange for some of those primes to get discarded. We can arrange for the starting point of our interval to be divisible by 4, because that y came from a congruence modulo an odd number. And therefore, we can impose an additional congruence condition mod a power of 2. Say we can arrange for the starting point of the interval to be divisible by 4. Then, of course, if j is 3 mod 4, then y plus j cannot be a sum of 2 squares. So if j is 3 mod 4, then 4j minus 1 is 11 mod 16. So primes in this range, in between 4/5 times k and 4k, which are 11 mod 16, we don't need them in the argument from above, because we know in those cases the number y plus j can't be a sum of 2 squares anyway. We don't have to do these considerations for those numbers from before. So in that product capital P, in that range for P, we can remove the primes in the residue class 11 mod 16. We don't need them. So this gives that improved upper bound for capital P, and that would already improve the 1/4 in Richard's result by 5/16. And now this idea can actually be further developed. You can also consider certain smaller intervals. And also congruence is not only mod 16, but modulo powers of 2 to the L tending to infinity. And actually these two go hand in hand. And let me just use a simple example to illustrate what's going on. So say we are now working mod 32, then in this interval mod 32, we can remove 3 residue classes. We can remove the residue classes 11, 23, 27, if P is a prime in between 4/5 k and 4k. And now let's move to that next smaller interval between 4/9 times k and 4/5 times k. Primes in that interval, they are actually needed twice in the argument, either if a 4j minus 1 is equal to P, or if a 4j minus 1 is equal to 5 times P. But there is still one congruence class, mod 32, we can remove in that intermediate interval from 4/9k to 4/5 times k, because that's the residue class 11 mod 32. If we're in the first case, P is 4j minus 1, we don't need the residue class 11 mod 32 anyway. This is similar to as before. But also in the second case, if P is congruent 11 mod 32 and we times 5, then we get the residue class 23 mod 32. And this is also one of the residue classes mod 32 we don't need. Why do we don't need that? If we arrange for the starting point of the interval to be divisible by 8, we can do that, then numbers y plus j can't be a sum of 2 squares if j is 6 mod 8. And this translates into 4j minus 1 being 23 mod 32. So in that interval here, between 4/9 times k and 4/5 times k, if p is 11 mod 32, that prime won't be needed either in the situation where 4j minus 1 is p or 4j minus 1 is equal to 5p. So we can throw away that residue class 11 mod 32 in that intermediate interval. And you can even go one step further for a smaller interval between 4/13 times k and 4/9 times k. And in fact, the optimal construction, this was found by a computer search, but it's possible. So we have a proof that can be verified by pen and paper in a few pages. So the initial construction was found by a computer. So for some strange reasons, I can't see the chat. Are there any questions so far?
No, we don't have any questions so far.
Oh yeah,
So we can continue. Okay.
Yeah. Thanks for letting me know, Himmer.
Okay.
So for general binary quadratic forms of discriminant D, we can use a similar idea. So here Richards considered that arithmetic progression. So for sums of two squares, D absolute value would be 4. And for a fixed D, R is a fixed number such that this Kronecker symbol here is -1. And then Richards in that product capital P, he used all the prime numbers at most dk, for which the Kronecker symbol is -1. So he considered half of the primes. And this is actually quite wasteful. So here we can use a similar trick. So at the upper end of the interval, I don't have to explain what these L's are. At the upper end of the interval, say P is in such a range, we only need primes which are in one residue class, namely R mod D. That's enough for the argument to work, rather than half of the primes. And then in the next smaller interval, say in this interval here, we only need primes falling into 2 residue classes modulo D, rather than all primes for which the Kronecker symbol is -1, and so on. This leads to some telescopic sum, and this provides a quite substantial saving. And this way we can improve that 1/D constant in the Richards result for general binary quadratic forms roughly by 1/2 times log D. So the ideas are very similar to what I presented before for sums of 2 squares. The details are a little bit more involved just to work it out. There's a second refinement, and we call this the probabilistic refinement. And this actually commutes with the modular refinement so far. Both of these two could have been done independently, and one can also combine them, and one gets even better results. So if we go back to the situation of sums of 2 squares, in that product here, that +1 is a little bit annoying, because in that product here, the main contribution, this is really coming from the large primes, so close to 4k or of order of magnitude k. And for those large primes, the beta p itself is 1. So adding 1 really squares that expression. So it would be nice to be able to get rid of the +1. And if we could do that, then roughly the size of p would shrink to its square root. And by taking the logarithm, this would lead to a doubling of the length of gaps we get. And this is actually doable. So as I said, for those large p around 4k or of size of order of magnitude k, the beta p is 1. And for those primes, we can remove the +1. And how can we do that? We needed to make sure that if the numbers we are considering are divisible by p, they are not divisible by p squared, because p is 3 mod 4, and divisibility by p has to exclude being a sum of two squares. So we can use a probabilistic idea. We can twiggle around that starting point y somewhat, and then this way we can choose it in such a way that if one of the numbers in this interval is divisible by a large prime p of order of magnitude k, then it's not divisible by p squared. This can be done by a probabilistic argument, which in fact is kind of a convergent sieve. And this way we can roughly reduce the size of that product p to its square root. So this is the second trick. Yeah, and then for those large p in the product, yeah, we can remove the +1, so the power gets removed from gets reduced from 2 to 1, and that leads to a size roughly the square root of what we had before. Okay, these are two of the main results I wanted to present. Just a quick comment, yeah, you can combine these two, the modular and the probabilistic refinement, and then in the case of binary quadratic forms for sums of two squares, we worked it out in detail, and that's the bound we got in the first main result. We could have also included a probabilistic refinement for the second result, general binary quadratic forms of discriminant D, but for the sake of simplicity, we didn't do it. It would lead to another a gain of a factor 2 in the size of gaps there. Okay, now in the second half of the talk, I want to move into a slightly different direction, but it's very much related. So this is kind of long gaps between sums of two squares in nonlinear intervals. What do I mean by that? Let's consider these class of polynomials. PD of x is CD plus x to the d. And if d is 1, then we are back to the previous case. We are interested in intervals. We want to find a CD such that we get a long string then of x's for which we won't hit a number which is the sum of two squares. And now we want to do it in a nonlinear interval. We want to find such a CD such that we get a long polynomial sequence of x's where we don't get a sum of two squares. Of course, there's trivial cases here to exclude. If d is 2 and the starting point CD is 1, then this expression is always a sum of two squares. By the way, this is a quite an amusing problem. So this year was a question in the most recent problem section of the American Mathematical Monthly. So the question was to show that for all odd n, this number 1 plus 7 to the n plus and so on plus 7 to the 6n, it's always a sum of two squares if n is odd. Yeah, so it could be that you end up with an expression which is always a sum of two squares anyway. But let's consider this question for a given degree d. Can we choose a CD such that we find a long sequence of numbers in that polynomial sequence, which is not a sum of two squares? And we get quite satisfying answers there. So for composite D, at least, we have a very complete answer to this question. So that's the third result today. Again, this is joint work by all these 5 authors. I just say this is missing from the statement of the theorem, but it's also joint work between all 5 of us. So if D is even and at least 4, then you can choose the constant CD to be 6, and then 6 plus x to the d is never a sum of two squares, regardless of x. If D is odd and composite, then you can do something similar. Then you can define Q to be the least prime factor of D. Then, of course, this is also odd. And you define CQ to be 2 if Q is 3 mod 4 and 6 if Q is 1 mod 4. And then you defined your starting point CD of the sequence to be this here, CQ times Q to the Q. And then this polynomial is never a sum of two squares, regardless of what X you plug in. So in these two cases, in A and B, you're able to find such a CD, such a starting to get an infinite, a gap of length infinity, where you never get a sum of two squares. So we can do prime cases if the exponent D is 2 or 3, then we can show it's impossible to find any fixed CD such that CD plus X to the D is never a sum of two squares. The proof of this result uses somewhat different tools, but let me quickly sketch how you can do this. This is actually elementary number theory. There's very little analytic number theory involved. The proof of part A is elementary. This can be done by congruences. If X is odd, then this polynomial 6 plus X to the D, if D is an even number, at least 4, then this polynomial 6 plus X to the D is congruent 3 mod 4 for odd X. And for even X, it's congruent 6 mod 8. So in both cases, you see it can't be a sum of two squares. So this is a straightforward exercise in elementary number theory. What is more interesting actually is the proof of part B. And this is motivated by work of Jaggi and Kaplansky from the mid-90s on Waring's problem for mixed exponents. They found counterexamples to the local global principle for Waring's problems for sums of two squares and the 9th power. So let's assume we are now in case B of the theorem. D is an odd exponent, which is a composite number. Q is the least prime factor of D, then Q is also odd. And because D is composite, that second factor D2 has to be bigger than 1. That's important. And now let's suppose we found some little z such that PD of z, let's call it capital N. It is that expression such that this is a sum of two squares. And we want now to contradict this statement. And this is also a proof which is in principle only elementary number theory, but it's more involved, it's more tricky. So let's just do one case. Let's do the case where that least prime factor Q is congruent 3 mod 4. The other case where it's 1 mod 4 is similar. In the case where Q is 3 mod 4, that CQ is 2. Then the first observation is the Z cannot be even, because if Z happened to be even, we could take out a factor 2 to the Q from the whole equation. So here CQ is 2, we can take out a 2 to the Q there, we get Q to the Q. And here the second expression, this is Z to the Q times D2 over 2 to the Q. If Z is even, we can take out that factor. And now D2 is bigger than 1. So the second expression, that Z to the Q D2 over 2 to the Q is still divisible by 4. And because Q is 3 mod 4, the first term gives the contribution 3 mod 4. So the whole thing is 3 mod 4. Therefore, N over 2 to the Q can't be a sum of two squares. And then N cannot be a sum of two squares. So that's impossible. So Z cannot be even. So Z is either 3 mod 4 or 1 mod 4. And the case 3 mod 4 is also easy to rule out. Then you can check your expression capital N. That would be 3 mod 4. And again, it couldn't be a sum of two squares. So therefore, the Z has to be 1 mod 4. Okay, and now we enter the tricky part. So this is our expression for N. Q is, if you look back, the Q was, the D was Q times D2. So you can factorize the whole thing. You can take out a factor 2Q plus Z to the D2 and you get another factor. Let's call these two factors N1 and N2. And now the first factor n1, this is congruent 3 mod 4, because the q was 3 mod 4 and the z was 1 mod 4. So therefore, that first factor n1 must be divisible by some prime number t, which is 3 mod 4, to an odd exponent, to an exact odd exponent. But now n1 is a factor of n, and n is the sum of two squares, as n1 is exactly divisible to an odd power by a prime t, which is 3 mod 4, that prime must also divide n2. So we found a prime t, which is 3 mod 4, dividing both the factors n1 and n2. And now because t divides the first factor n1, we know 2q is congruent minus z to the d2 mod t. And then we can go into that representation at the top. We can plug it in. We can plug in for 2q minus z to the d2 mod t. And after simplification, we find we get that bottom line. And this is just q times z to the d minus d2 modulo t. So as t divides n2, it has to divide either q or z. Okay, so let's first discuss the case where t divides q, then also t divides z, because t divides that number 2q plus z to the d2, which is n1. And now the exponent d2 is bigger than 1, and q was a prime number. So as t divides that expression, it exactly divides it to power 1, to no other higher power. On the other hand, t exactly divides n2, the other factor, to an even power. You can check each of the summands. N2 was the sum of terms of the form 2q to the I minus 1 and so on. Each of those terms is divisible by q to the q minus 1. And all of those summands except exactly 1 are even divisible by q to the q. So q minus 1 is the exact power of t dividing the second factor n2, and 1 is the exact power of t dividing the first factor n1. This is the type where t to the q exactly divides. And 1 is the exact power of t dividing n1. So the exact power of t dividing the product n1 and 2, which is n, is q. And as q is the prime 3 mod 4, that's a contradiction to n being a sum of two squares. It can't be divisible by a prime 3 mod 4 to an exact odd power. So t dividing q is impossible, so t does not divide q. And now if you go back to formula 4, if t does not divide q, it has to divide z, because t divides n2. So t divides z, and then t has to divide 2q, because it divides the sum 2q plus z to the d2. As t does not divide q, then it has to be 2. And that's a contradiction to 3 mod, to t being 3 mod 4. So that's the proof for part B. I'm sure there's a more conceptual way of doing it, making use of Brouwer-Mannion obstruction type stuff, but you can do this in a completely elementary way. And the proof of part C actually is completely elementary. You can use a trick in the cubic case of Elkies, Kaplansky, and Adler there. They've shown every integer, say every positive integer is a sum of two squares and a cube, where actually the cube is negative. And this you can show by using a finite set of congruences covering all the cases. So here you cover all the possible residue classes, mod 32. So whatever starting point n you choose, you can find a negative z cube, and then n minus z cube will be equal to a sum of two squares. So this settles part C of the theorem, and actually a similar but easier argument works for the exponent too. So also there you can use an explicit parametrization. So there's one open conjecture. This we can't show, but we conjecture it in general. If D is a prime, whenever D is a prime, we can only prove it for 2 and 3. Then you can't find any constant CD such that the polynomial CD plus x to D is never a sum of two squares. I guess that's probably a quite hard question to settle. So what is left is the case of prime exponents here bigger than 3. And for those, we can, similar to the Richards result, we can show there are long gaps in the polynomial sequence PD of x there. This is the last result. This is on that slide here. So if D is an odd prime, let's fix it. Then for any gap length k, you can find a starting point yk such that in that polynomial sequence yk plus j to the d, j running in that interval of size k, none of the numbers is the sum of 2 squares. And as before, you get such a lim sup for the length of that gap. You can bound it by that rather complicated expression here, but this is not so hard to estimate. So say if epsilon is any given positive constant and d is sufficiently large in terms of epsilon, you can simplify that expression. CR is the famous Landau-Ramanujan constant. So Landau's result on the asymptotics of the number of numbers up to x, which are sums of two squares. And we also have an explicit result if the degree is at least 17. We get this bound here. The constant is actually worse than in the asymptotic result, but the advantage here, so this was just an asymptotic having that epsilon, and here this is completely explicit if the degree is at least 17. So I guess I'm now running out of time, so I only want to briefly, very briefly show the remaining slides. So the idea of proof here is similar to what we've done before. This elaborates on the original approach by Richards. The congruence stuff is a little bit more complicated. We need some lemma dealing with GCDs occurring in the auxiliary congruences. We use a similar construction for that product capital P, but it's more complicated. We have a part where we use small primes up to size 4k and larger primes up to size 4kd. So here you can regard this as the product P times M is at most 4kd, but there's an extra congruence condition on the primes which helps, which saves you quite a lot. I don't have time to go into the technicalities here, but then the idea is pretty much the same. You find the starting point y by an auxiliary congruence. You can use similar arguments as before to show that none of the integers in the resulting nonlinear interval then is a sum of 2 squares. And then you have to use some analytic number theory to bound above the size of that product, and this gives you a lower bound for the size of your gap. And if you want explicit results, you need to bound those sums over odd m's at most d-1, which are sums of 2 squares, 1 over m. You can get results by partial summation from Landau's result, but if you want more explicit stuff, then you need some numerical bounds for the error terms. And there we found some paper by Peter Maury and Theorem actually quite useful to get these two lemmas, which are more explicit. So especially the second one, this is very explicit. You need to make explicit the error terms in Landau's theorem there, and this we imported from the results by Maury and Theorem. Okay, but I guess I'm now certainly out of time. So thanks a lot for your attention.
Thank you very much, Dietmann. Well, you gave us a lot of information here, but let's start by thank you very much. And well, it's easy to see that's why you need five authors here, because it's a combination of a lot of good ideas that have to come together to get these wonderful results. Well, congratulations to you, all 5 of you.
Thank you very much.
But this is even, I think for me, it's even harder hard to ask questions about this because there are so much technical questions but I can at least appreciate the quality of the results. They are really wonderful and very, very impressive.